Hope everybody's doing well this morning. I will be recording this session and putting it online for everyone to look at later. Don't forget your homework is due tonight.
So 2.
All right, all of you that are logged into Learning Catalytics have answered, so I'll go ahead and show the results. More of you that are here, if you'll log in and get going this morning, we can have more responses. The correct answers are, and the answer key is actually wrong here, and I'll go back in and fix it later to give you credit. The correct answers are B and E, so 50% of you did get this correct. Let's talk about why that is. So if I'm going to check for continuity, I need to check that f of x doesn't skip values where it changes functions. That's the main thing I need to be concerned about. So you can see that we change from the function 2 to the x to the function 3 minus x at x equal to 1. So if I look, I've got 2 to the 1 is 2. I'm going to compare that with 3 minus 1, which is also 2. So it seems like they match up in value, right? They're both 2. But why is this discontinuous at 1? Does anybody want to say? So even though they match values at 1, why is it still discontinuous there?
Oh, because there's a less than sign, there's no equal sign there.
Yeah.
It's an open hole.
Right. The function value at 2 doesn't exist.
That makes sense.
So even though the limit as x goes to 1 of this function turns out to be 2, the function value at 1 doesn't exist. So it can't be continuous at 1 because you have to have the function value match the limit. The other place where it changes graphs is at 4. So if I look at 4, so this is what's going on at x equal to 1. If I look at what's going on at x equal to 4, I've got 3 minus 4 is negative 1, and I'm going to compare that with the other function, which is square root of 4, which is 2. These don't match. So we would say that the limit as x approaches 4 of this function doesn't exist. So if the limit doesn't exist, it can't be continuous. So this is the kind of thing that you would be checking for these sorts of problems in the future. All right, let's move on to a second example. Feel free if y'all have questions to let me know. The second example deals with finding asymptotes, horizontal and vertical asymptotes. We talked about that in Wednesday's class. So give it a look and see what you think. So this is another one of those check all that apply. So there's multiple correct answers here. Check all of them that are correct. There you go, Sean. Can you see it now? All right, I'll give you about another 20 seconds or so. All right, the correct answer on this problem is A, B, and D. I noticed that 100% of you that responded put D. If you put D, then by definition, the function has a horizontal asymptote. Because if your limit at infinity is equal to a number, which you're telling me D is correct, the limit at infinity is equal to a number, that number is the horizontal asymptote. So let's take a look at it together real quick and remind you of a couple of the results from Wednesday's class. So if this is our function, if we're looking for a vertical asymptote, then we're looking for places where the denominator is 0. So I'm going to set the denominator equal to 0 and solve for x. So the cube root of 1/2 is my vertical asymptote. And the reason I know it's a vertical asymptote is it's a value that makes the denominator 0, but if you plug this number into the numerator, it doesn't also make the numerator 0. So I know that A is correct. I know it has a vertical asymptote. All right, since this is a rational function, then I know any horizontal asymptote it has comes from that theorem that we ended class with last time. That had 3 different cases. If you look on this particular problem, the degree of the numerator, remember the degree is the highest power. So the degree of the numerator is 1 because the highest power of x in the numerator is 1. Similarly, the degree of the denominator is 3 because 3 is the highest power in the denominator. So if you go back and look at that theorem, if you have a higher polynomial degree in the bottom than you do the top, then over time the fraction will get smaller and smaller and the limit is 0. So by the 3 cases theorem that we had in class, the limit as x approaches infinity for this function turns out to be 0, since the degree of p of x being the numerator, is less than the degree of q of x, which is the denominator polynomial. So make sure that you know that theorem very well. You're definitely going to have examples like that on the exam over this unit, where you have to use that theorem to determine if you have a horizontal asymptote. So finally, because the limit at infinity is finite and it exists, then that implies that y equal to 0 is a horizontal asymptote for this function. All right. The exam is at the end of module 3, so we're doing module 2 right now. Module 3 is a 2-week module, so it'll be 2 weeks from this coming Friday. 2 weeks from today, actually. That's when the exam is. All right. So what I want to do now with you is to look at several limit problems. We haven't done a lot of these in class yet. Calculating algebraically the answer to limit problems that involve infinity somehow. So what I want to remind you of for this particular problem, this involves the arctangent function. And we talked about the arctangent function in class together right at the end as an example of a function that has 2 different horizontal asymptotes. So let me just remind you of what that graph looks like for a second. So it has one horizontal asymptote at negative pi halves. It has another horizontal asymptote at pi halves. And the graph of the arctangent function looks like this. So tangent inverse, arctangent, the graph looks like this. So based on that knowledge, I want you to try to answer this limit problem.
I'm having a bit of trouble with it. It's only let me select one. I'm not sure if anybody else is having the same problem.
There's only one answer here on this one.
Okay. All right.
I'll give you about another 30 seconds. All right, everyone logged in has responded. The correct answer is G, pi halves. So let's talk about why that is. If you look at the limit problem itself, remember our rules, our limit laws say that if the function is continuous, which arctangent is, then you can bring the limit inside the function. And so I'm looking here at what the limit of the cubic is. So we kind of know what a cubic function looks like, right? Cubic function looks kind of like that. Actually, that looks a little bit more like tangent, but it's close. So this is kind of like x cubed. What we know about x cubed is that it has this sort of ending behavior. So as you go toward infinity, x cubed goes to infinity. So since this is a cubic function, at infinity, its ending behavior is infinite. So I know that whatever the number is in here, it approaches infinity. So this is basically telling me, or basically saying the same thing as what happens to the inverse tangent function as whatever is inside the inverse tangent function goes to infinity. So these say the same things. You know, you can technically write down if you wanted to. You could write this down. A lot of mathematicians consider that to be kind of inappropriate because you can't technically plug in infinity. Infinity is always a limiting process. But if you want to think of it this way, you can. So just understand that you're talking about the ending behavior of the arctangent function, which if you look at the graph that we had here, the arctangent function, as x goes to infinity, it gets closer and closer to the asymptote pi halves. So there's knowledge of two functions that are required here to do this problem. You have to know what a cubic function looks like, and you have to know what arctangent looks like. And that's going to be common for a lot of these infinite limit problems. You have to know the basic ending behaviors that you learned about in pre-calculus for a lot of these graphs. All right, let's try another one.
I got one question, sir.
Yes.
How would you? Why would you need to know what the cubic? I mean, the function looks. I mean, you showed the graph earlier. If you kind of scroll down a little bit, I mean, it looks like you're just going to pi halves there on the right. I mean, why do you need to know about the cubic function? Wouldn't it just mirror the same way, kind of? I mean,
well, you just need to know that the thing inside of it, because what if this function inside of it was negative x cubed? Right? If that function inside of it was negative x cubed, then the cubic function would look like this. And so as it goes to infinity, this function would go to negative infinity. So you would have negative infinity inside the tangent inverse function, which would push it toward negative pi halves, not positive pi halves.
okay.
So you have to know where that inner function is heading.
Okay, I understand. Thank you, sir.
All right, let's try another one. This one looks complicated. I'll give you a little bit of a hint here. When we were talking about the three cases theorem and we were doing an example that had a rational function, we divided the top and the bottom by the highest power. That is a trick which works in a lot of cases, not just that one. So I'll give you a little bit of time to dig into this one, but my hint is to divide the numerator and denominator by the highest power that you see.
Excuse me, Dr. Erkey.
Yes,
You were saying our math exam was going to be on September 25th, correct?
I believe that's correct. 2 weeks from now. Is there an issue with that?
No, sir. I was just making sure I write it down on my calendar.
Okay. Yeah,
Thank you.
it should be up on Canvas. The assignment for the exam's up. I don't think I have the review up yet, but that'll probably go up next week.
Yes, sir. Thank you.
Sir, I got a question.
Yes.
When you say the highest power, do you mean highest, like the highest number value, or like the most positive number?
Well, yeah, you should treat a negative as being smaller than a positive, right? So the positive power would be larger.
Okay.
These negative powers are decaying exponentials, so they get really small as x gets big. I want the thing, you need to divide by the thing that gets the biggest, right? So what term on the top and bottom gets the biggest as x goes to infinity? Divide through by that term.
Okay.
All right, I'll give you about another 30 seconds on this one. I know this one takes a little bit longer to do all the work. I'm going to talk about, when we go over this one, I'm going to talk about how you can just look at it and know the answer as well. Although I do want you to get in the habit of doing work even when you think you know what the answer is. All right, so the correct answer here is infinity. I'm going to do it first sort of intuitively, and then I'm going to show that that answer is correct. So the intuitive way to think about this particular one is to take and look at what happens as x goes to infinity of each term. So if I look at that, I know that, so I'm kind of thinking about directly substituting here. I know that all of these decaying exponential terms, all these that have negative exponents, the graph of a decaying exponential looks like this. So this is the graph of e to the minus rx for any value of r greater than 0. So it decays down to 0. So I know that realistically, this thing is going to look like e6 to the infinity minus all of these that decay are going to be 0. So realistically, this thing is e to the 6x over 2e to the 3x out at infinity. Like this is the graph that actually is happening out there. And so intuitively what you can think is, well, e to the 6x grows much faster than e to the 3x. So this fraction as a whole, as you go out to infinity, the top is going to be much bigger than the bottom. So this thing's going to grow to infinity. So that's the intuition here, is that all of the decaying terms go to 0. And then what's left, e to the 6x, is much bigger than 2e to the 3x. So that's why the answer is infinity, but let's show it. So let's kind of prove that that's the case. I said or suggested that you should divide by the highest power, which is e to the 6x. So I'm going to take what I have here and divide every term by that power. Remember, when you divide an exponential function by another exponential function, you subtract their exponents. So when I divide through by e to the 6x, I'm going to be subtracting 6x from every exponent. So I get 1 for the first one, and then subtract 6x, you get minus 12x. Subtract 6x, you get minus 3x, minus 15x, minus 9x. So after you've divided through by e to the 6x on both the top and the bottom, this is what you have. So what you can see now is if you try to evaluate at infinity, all of the decaying exponentials are going to go to 0. So you'll be left with 1 minus 0 over 0 minus 0 plus 0, which is 1 over 0, which we know tends to infinity. The only thing you might be concerned about here is whether it's positive or negative infinity. But understand that this term, the 2e to the negative 3x term, remains the largest, and that term is a positive term. So you're going to have positive values in the denominator as it approaches 0. So the correct answer here is infinity. Those tend to be trickier. These problems involve a bunch of exponentials like that, but the intuition should let you know right away kind of what the biggest term is, and then whatever the biggest term is, if the biggest term is in the numerator, then the answer is infinity or negative infinity. And if the biggest term is in the denominator, then the answer is 0. It's kind of like the rational function theorem that we looked at in class. All right, let's try another one. Give us about another minute or so. This one could be a little tricky. Algebraically, knowing how to deal with square roots is the main thing here. This is not a problem where you use a conjugate, though. All right, all of the answers are in. Turns out the correct answer is C, 2 over square root 5. I'm not surprised a lot of you put 2/5. That's kind of the reason I'm doing this question with you, is I want you to see where both those answers could potentially be coming from. So if this is our limit problem, if I immediately try to plug in infinity, you can see I get infinity over infinity. So this is an indeterminate form. I can't just directly put in the limit and call it a day. So I've got to find some algebra that I can do here to simplify this somehow. And it turns out that the algebra that you need here is one that students often forget to do. And that is, if you have a square root on one part of a problem like this, you can make the whole problem a square root by squaring the top and then putting it under the same square root. So that's what I'm going to do. This is the same thing as if I square the top, it's 4x squared. And now I have the entire problem under one square root. So this is a trick that a lot of students forget that they can do. And it's really helpful here, but because you've got the square root of the whole thing, we can use our limit laws, which say that square roots can, or that limits can pass inside of square roots. So I can now bring the limit inside of the square root. And what I have at that point is something that we should recognize. I'm now taking the limit of a rational function. So this is a rational function where the degree of the top is 2. The degree of the bottom is also 2. Because the degrees match, then the limit is whatever the ratio of the leading terms are. Now be careful here. 2 is not the leading term. The definition of the leading term is the term that's in front of the highest power. So since x squared is the highest power, 5 is the leading term or the leading coefficient. So the three-case theorem says that if you take the limit at infinity of a rational function where the degree of the top and the bottom are the same, you get the ratio of those leading terms, which turns out to be 4/5. So the answer here is the square root of 4/5, and that reduces the square root of 4 over the square root of 5, which is 2 over square root of 5, which is the correct answer.
So you said, I'm having a little bit of trouble with the algebra there. You say you can square the entire function?
So this 2x that's right here, so if you take 2x and square it, you get 4x squared, right?
Yeah.
So the square root of 4x squared is the same thing as 2x, yes?
Yes. Wouldn't you square the bottom too, though? Or
No, the bottom already has a square root. So if you take this, if you have the square root of a divided by b, that's the same thing as the square root of a divided by the square root of b.
okay.
So I have a square root in the bottom. I'm writing the top function 2x as though it's a square root itself. And then that would give me a square root on top, square root on bottom. So I can write that as one big square root.
Oh, I understand now. Okay, thank you.
Are there any other questions on that problem?
Quick question. in the denominator, you have 2 plus 5x squared. What happens to that plus 2? Does it just...
Well, I'm using that three cases theorem. So
Okay.
the three cases theorem tells us that if you have a rational function, which this is a rational function, that if the degree of the top and the bottom are the same, then the limit of the whole thing, including the two, right? The limit of the whole thing is whatever the ratio of those leading terms is. So I'm not plugging infinity in and looking at the limit of each piece. I could do that, but I'm just using that theorem from class.
Yes, sir.
Let me pull that theorem up for y'all real quick. So I'm using this theorem from class on Wednesday, the three cases theorem. So we're in the case where the degree of the numerator is equal to the degree of the denominator. So the limit then is equal to the ratio of the leading coefficients. So if you look back at your notes from Wednesday, that's what I'm applying there.
Yes, sir. Thank you.
All right, let's look at one more, and then we'll call it a week. All right, so the last one here to look at is this limit. I'll give you, let's see, about 4 minutes, 3 minutes, 4 minutes to try this one out and see where we are. I see a lot of people putting 0 right now. I'm not saying 0's wrong. I'm just saying if your reasoning for 0 is you think infinity minus infinity is 0, remember that's not the case. Infinity minus infinity is an indeterminate form. It could be 0, it could be 2, it could be infinity, it could be a lot of things, but don't just assume that infinity minus infinity is 0. But I'm not saying 0 is wrong. I just be careful about that. All right, everyone has responded. The correct answer here is 0, but once again, it's not because infinity minus infinity is 0. We're going to have to show the work to show that this is indeed the correct answer. I saved the trickiest one for last here. This is of the form a minus the square root of b. So if you remember from about a week ago, we were talking about how to handle limits of that type. You use the conjugate. So the conjugate of this is a plus square root of b. So if I directly substitute in, you will get infinity minus infinity. This is indeterminate. It can never be an answer in the class. And even though sometimes it's 0, it's not always 0, so I can't just say it's 0 and call it a day. You might have lucked out on this problem, but there'll be other problems where it's not 0. So I want to instead apply the conjugate. So I'm going to multiply the top and bottom by x plus that square root. And so remember how this works. If you have a function times its conjugate, so a minus square root of b times a plus square root of b, you square the first term, you square the second term, and you subtract them. So I'm going to, x squared is the first term. I'm going to square the second term, which gets rid of the square root, and then I'm going to subtract them. So that's what the numerator turns out to be. The denominator here, well, this function is technically divided by 1. So the denominator here is 1 times this thing. So the advice that I've given in the past is not to try to combine anything on the bottom. So I'm just going to leave the bottom as it is. Now I'm looking for a cancellation to occur. And if you notice, I get x squared minus x squared here. So I do get a cancellation. Be careful here, the negative distributes. So you do get x squared minus x squared, but you also have a negative 7 that's left. Right, so now that we managed to cancel out the x squared terms, you should, after you get a cancellation, you should always retry the limit. So if I try evaluating at infinity, notice there are no x terms in the numerator. All of the x's are in the denominator. Everything here is positive. So this is going to be negative. This is going to converge to negative 7 over infinity, which we know is 0. It's negative 7 over a really large number. That number keeps getting bigger. This fraction keeps getting smaller. It converges to 0. So the correct answer here is 0. So even for these limits that involve infinity, you can still do this conjugate method that we talked about, provided that you do have a conjugate, like a minus square root of b, a plus square root of b, square root of a plus square root of b, some sort of conjugate problem approach. Do y'all have any questions about this one?
Yeah, I'm just a little confused at how we got negative 7 over infinity from negative 7 over x plus x squared plus 7.
Yeah, sure. What I'm essentially doing, right, when you evaluate the limit, I'm directly substituting here is what I'm doing. Okay. So if I take the x goes to infinity, right, all of these x terms in the denominator are going to become infinitely large.
Yeah.
So you have infinity squared plus 7, that's infinitely large. The square root of something that's infinitely large is still infinitely large. And then you're adding it to infinity, which is still infinitely large. So the number that's produced in the bottom here, as we plug in bigger and bigger x's, that number just keeps getting bigger.
Okay.
And so as a limit, the denominator limits to or converges to infinity. It just keeps getting bigger.
Okay.
And so as a whole, the fraction keeps getting smaller because as all of this is going on in the denominator, the numerator is not changing. The numerator is just -7. So you're talking about like -7 divided by a billion, -7 divided by a trillion.
Mm.
The fraction as a whole gets smaller.
Okay, thank you.
Yeah. Any other questions? All right, well, that's a great place to stop today. Blessings on your weekend. Hope everybody's doing well. Don't forget about the homework due tonight. I'll see you all back in class on Monday.
Have a good weekend, sir.
You too.